All right, the equilibrium constant K. When we talked about K in rates, in terms of rate law equations, it got a little complicated. So you'll be happy to know that when we talk about the equilibrium constant K, we're talking about the same K, but we don't have to worry about the units. So we assume that all of our reactions are an elementary process. Because of that, we can set up a rate law expression for the forward reaction and the reverse reaction. So here I've used a Kf to be the rate law constant for the forward and a Kr for the reverse reaction rate law constant. And so I've set, because it's an elementary process, the coefficients are the exponents. So for the forward reaction, our reactants is NOBr and coefficient 2, so it's second order. For the reverse reaction, the reactants will be our products. So it is second order with respect to NO and first order with respect to Br2. But we know at equilibrium that the rate of our forward reaction is equal to the rate of our reverse reaction. So we can set these two expressions to be equal to each other. So we can set this reaction to be equal to this reaction. So K forward times NOBr to the second order is equal to Kr to N times NO to the second order Br2 to the first order. Now, a constant divided by a constant is a constant. So if we move our K's to one side, so let's say the lefts, we will bring this Kr to this side. That means we want to get all of our concentration terms to the same side. So we're going to move this to the other side. So in order to move this over, we would have to divide. So it ends up in the denominator over here. And so now we have Kf over Kr is equal to NO to the second order Br2 to the first order over NOBr to the second order. So, because these two are constants, we get a new constant. And basically, this represents the equilibrium constant for this reaction. So basically, when you write your K expression for a system at equilibrium, it is going to be K will be equal to the concentration of the products, right? On the right-hand side on the products, we have NO and Br2, and they are on top, over the concentration of your reactants. This is on the bottom. And the coefficients are the exponents. So this allows us to take a look at the ratio of our products to our reactants, which is useful because it will actually tell us whether our equilibrium favors our products, whether equilibrium favors our reactants, so whether or not it lies to the right, favoring products, or lies to the left, favoring reactants. So right and left mean right and left of the arrows. So if it favors the right-hand side, it favors products, favors the left-hand side, it favors reactants. And that will mean their quantity in this ratio will be larger. So if it favors reactants, you're dividing by a large number, so K is going to be very small. If it favors the products, your products are going to be a larger number. A larger number divided by a smaller number is a large number. So if the reaction favors products, your K will be a large number. It will be greater than 1. So this is called law of mass action, and this is expressing the relative concentrations of the reactants and products at equilibrium in terms of a quantity called the equilibrium constant. Okay, so you have a reaction, just a general reaction, and it will be the products over the reactants, but you can only put in values that are subscripts AQ and gas state. These are the only two you can put in, and that is because if you have a solid or a liquid, the amount doesn't change very much, so they pretty much stay constant, so they become part of the K. So your equilibrium expression, you can only put anything in that's AQ subscript or a gas subscript. And we'll get into practice writing them. So, notes, important things. The square brackets with the letters inside means concentration, and it's moles per liter. K is constant for a specific reaction at a given temperature, just like kinetics. So if you change the temperature, you've got a new K for the same reaction. You can calculate K if you know all the equilibrium concentrations. In general, the equilibrium constant for the forward reaction is the reciprocal of the constant for the reverse. So if K is 2 for the forward reaction, for the reverse reaction, it's going to be a half. Homogeneous equilibrium. This means all entities are in the same phase, so all gases. Heterogeneous means you've got gases and solutions, AQ. Concentration of a pure liquid or solid is part of K, just like I mentioned. So here in this example, liquid water isn't going to really change very much. So initially you would think to write H2 second order, O2 first order, all over H2O to the second order. But because that is so constant, it becomes part of the K. Could multiply by K to give you a new K. So your actual K expression would be just the entities having gas subscript, which can be a bit tricky. If this was reversed and you had H2 plus O2 going to H2O liquid, then your K expression would be 1 over H2 second order O2. So be careful. And equilibrium law expressions are written from net ionic equations. So balance your equations with simplest whole number coefficients and then remove any spectator ions. Your spectator ions will not go into the K expression. Because the mass action expression is written with the product concentrations in the numerator, K value gives you a direct indication of how far the reaction has proceeded. So this is what I was talking to you about, whether it favors the products or favors the reactants. So if K is less than 1, you have more reactants. It favors the reactants than the products. If K is greater than 1, you have more products because it's products over reactants. And if it's approximately 1, you've got equal amounts. And that comes from the fact that it is K products over reactants. Okay, so write the K expression for this. Well, they're all gas states, so they're all going to be in. So K is going to be equal to, and we put the products, HI. Coefficient is 2, so it's second order. And then on the bottom, concentration of I2, concentration of H2. They're both first order. So this is your K expression for this reaction. Okay, example number 2. We have this reaction, and it's already in a net ionic. And we have 3 AQ subscripts, 1 solid. The solid will not go into the K expression, so the I2 solid will not be there. So K is still products over reactants, so it's iron 2 plus over iron 3 plus times I negative 1 second order. So sometimes you're going to have elements that don't seem to be balanced in your K expression. Don't worry about it. It's not about balancing. The chemical equation is balanced. Solids cannot be in your K expression. Here, you've been given a K expression, and you need to come up with a balanced chemical equation. So go from a K expression to a reaction. Well, remember it's products over reactants. So on the right hand side of our arrow, we will have water, vapor. Our exponent becomes our coefficient. And then on the bottom we have our reactants, so hydrogen, and it was second order. So the coefficient is 2, and then it's first order with respect to oxygen. So you can go from a K expression to a chemical reaction. Now, if you look at this example, so the example here is take this reaction and put it into a K expression. So first of all, you should notice that it's a single arrow reaction. And there will be a case here where we have ions from the same element on both sides. So this isn't balanced either. We've got 2 chlorines on the left, 3 on the right. So first thing I want you to do is balance it. So we would need 3 of these, 2 of these. All right. Now, net ionic equation. So a total ionic equation would be 3 copper 2 pluses. So you split apart your AQ substances into their ions. So chloride ions. Write your ion first so you're not tricked into writing the wrong thing down. Copper 2 plus or 1 plus, in this case it's copper 2 plus. We know that from the formula. There's 2 chlorines. Chloride is not Cl2, that's chlorine. The chloride ion is Cl1 minus. So there's a total of 6 chlorines altogether. Aluminum stays the same. When you're writing your total ionic equation, all you're doing is you're splitting up your AQ substances into their ions. So this becomes 2Al3 plus and 6 Cl minuses plus 3 Cu solids. All right, so now if we look at this, we have a spectator ion. A spectator ion appears on both sides of the arrow. So there's our arrow. And therefore cancel. They're not involved in the overall reaction. So our chlorides cancel. Now, that leaves us with our net ionic equation. 3 copper 2 pluses plus 2 aluminum solids. Now we can have our arrows. 2 aluminum 3 plus and 3 copper solids. Now for our K expression, you can only have AQs. You can't have solids. So our K expression would be our aluminum ion, second order, over our copper ion to the third order. So we went from this all the way to just this. So write out a total ionic. If you can't see what the spectator ion will be, that will help you identify it. Then write your net ionic with a double arrow. And then from that, you will take your AQs and put them into your K expression. Okay, here's an example of what happens when you can actually find the value of your K. So we have this reaction, nitrogen plus chlorine gas reacts to form nitrogen trichloride. And at equilibrium, we have these three concentrations for the substances. So when you write your K expression, always show this part first. Write out your K expression properly first. So products over reactants. And then put in your values and do your math. So 0.19 will be squared, and to 0.0014. I'm not putting my units in because we don't need to have our units, which you'll be very happy about. So this is equal to 3.0 times 10 to the 8. So this is really a lot larger than 1. So the large K value tells you that products are favored. So in this case, there's a lot of product, nitrogen trichloride, and so we would say the reaction, the equilibrium lies to the right. Equilibrium favors the products.